Hi, everybody. This is Professor Reitz, Math2571, which is Introduction to Proofs. And this is Lesson 2. We're learning about sets and basic set theory. And today's lesson is about Cartesian products and subsets. So those are the two big ideas. And we're going to start off with this idea of Cartesian products. This gives us a way of doing something like multiplying two sets together. Now, sets are not exactly numbers, but if you think about what you went through when you learned about numbers, first you learned what they were, and then you learned various operations on them. We're doing a similar thing here with sets. We learned what they were last time. A set is a collection of stuff. And now we're learning some operations that we can do on it. Cartesian products and subsets are sort of two of those operations to consider. But to get started, in order to make this product notion make sense, we really need to talk about ordered pairs. So that's where we're going to begin. All of these definitions and theorems do appear in the lesson materials above this video, but I've reproduced them here as well. So ordered pairs are an idea that you are very familiar with. What is an ordered pair? Well, an ordered pair is just a list of two things, x comma y. And what do? We enclose it in parentheses and we separate the things by a comma. That's how you know you're dealing with an ordered pair. And what makes an ordered pair different than a set? It's just that in an ordered pair, the order matters. In a set with two elements x and y, there's no sense of one of them coming first and the other coming second. But in an ordered pair, when it's indicated by these round parentheses, well, there's the first and there's the second elements of it. This is useful because it lets us consider things in order, and we'll see exactly how that comes into play. So ordered pairs are something you're very familiar with. These are exactly like the x and y coordinates of the Cartesian plane. Cartesian has that root word of Descartes in it, Cartesian, which is also where the Cartesian plane and also the Cartesian product, which is the set theory operation, comes from. All right. So what is the Cartesian product? Well, the idea is if you have two sets, A and B, then the Cartesian product of two sets is going to be a new set. And I'm looking at the definition here. This definition is this is like one of the most important parts of today's lecture. And in particular, this second line right here, this is the real heart of the matter because it tells you what does the Cartesian product mean? What is the definition of it? So what is it? It's if you have two sets, a set capital A and a set capital B, well, when you take the product, we write it like this, A times B. We just use that same times sign that you would have learned back in elementary school. A times B, this is a new set. It's different than the sets A and B were to begin with. And this new set is defined as follows. A times B, what is it equal to? Well, it's a set. So that's those set squiggly brackets, curly brackets, say that it's a set. And inside we have set builder notation. And on the right-hand side is like conditions on various things. And then this is what you do to those things in order to put an element into the set. And what this is saying is if you take any element of the set capital A, pick an element of A and call it little a, and similarly pick an element of B and call it little b, well, if you just combine those two elements into an ordered pair where A comes first and B comes second, then that ordered pair is a member of this product. A times B, the Cartesian product of A and capital B. And what is the Cartesian product? The Cartesian product is, well, it's just all of the possible different ordered pairs you can make where the first element comes from A and the second element comes from B. And that first and second is important because when we write this product, A times B, A comes first and B comes second. And you can tell when we give an element of it, parentheses A comma B. Of course, here we're using the same letter, just the lowercase instead of capital. But in general, these are going to be numbers or any of a number of other things. And it won't always be obvious by looking at them from the notation, but the notation is arranged in this way so that the first item in the ordered pair comes from the first set, the one that comes before the times, and the one that comes after the times, that's where the second item in the ordered pair comes from. And it's just like when we talk about xy coordinates of a point on the plane, the x always comes first and the y always comes second. Okay. So that's the idea behind the ordered pair and the Cartesian product. What is the Cartesian product of two sets? If you have two sets A and B, well, the Cartesian product is a new set, A times B. So let's go ahead and do some examples. We're going to look at these first three examples, 1 through 3. I'm just going to pull a copy of these down below so that we can work on them. Whoopsie. I think I lost my selection before I completed it there. We're going to try it again. Whee. Okay, let me try again. Oh, no, that didn't work either. Okay. I hope to get much better at notability over the course of this semester. You guys can let me know at the end how I've done. Okay, so let's go ahead and put that. Here's our examples, and we're going to do them just one at a time. So let's focus on the first one. Here we go. So, if the set A consists of 3 letters P, Q, and R, and the set B consists of 2 letters W and X, find A cross B, or A times B. And here's the answer. We know that I need a pencil. Here we go. We know that A times B, the product of A and B, what is that thing equal to? Well, it's equal to a set, so I'm going to write it in squirrely brackets. Curly brackets, they're not squirrely. And inside, we're going to put all things that are ordered pairs, where the first element comes from A and the second element comes from B. So we might have the ordered pair P, that's an element of A, comma W, that's an element of B. Now, this ordered pair, although it consists of a bunch of symbols, a parentheses, a P, a comma, a W, and an N parenthesis, this is one item, one element in this set. So far, this product has one thing in it, this ordered pair. It has more than that, so we're going to add more stuff to it, but the other things are also all going to be ordered pairs. So another ordered pair is, we could put in P, comma, X, because P is from the first set and X is from the second set, and that's an ordered pair, P, comma, X. We can put in the ordered pair Q, comma, W. This is just picking a different element of the set A, and then going back to the element W there from the set B. I'm continuing on a new line here, so then we can put in Q, comma, X. And we can put in, let me see, what else do we have here? Well, R, comma, W, and also R, comma, X. Now, you can look through A and B and try to figure out if there are any combinations that I missed. Remember, I'm not allowed to put something from B in the first slot. I have to put something from A in the first slot. So that means I'm limited to P, Q, and R in my first slots here. And in the second slots, in the second position, I have to get something from B, which means I have to have either a W or an X in the second slot here. And I think this is all the combinations that there are of the things from A and things from B. These are all of the ordered pairs I can get, and so I'm just going to end this set by putting a close curly set bracket. Think of this as being just a little too long for one line, so it looks like this. What is A times B, the Cartesian product of A and B? Well, it's equal to the set containing the ordered pair P, comma, W, the ordered pair P, comma, X, the ordered pair Q, comma, W, the ordered pair Q, comma, X, the ordered pair R, comma, W, the ordered pair R, comma, X, and then that's it. So this is the set A times B. One more observation I'm going to make is just what is the cardinality of this set A times B? Well, the set A times B is a set of ordered pairs, and how many ordered pairs are there in here separated by commas? And if we count them up, there are 6. So this is equal to 6. Cool. One more observation before we go on, as this is going to be important later, is that this is no coincidence that this came out to be 6. In general, if you have A and B are finite sets, you'll notice here we had the size of A was 3 and the size of B was 2. Size and cardinality are just two ways of saying the same thing. And you'll notice that when you take the product of A and B, and you look at the size, the cardinality of the product, it's exactly equal to what you get when you take the cardinality of the first set and you multiply by the cardinality of the second set. So this A times B is just equal to the size of A, that's 3, times the size of B, and that's captured in general in this rule. The size of A times B is equal to whatever the size of A is times whatever the size of B is. I could have written a little x here for times. I just wanted to make a strong distinction between the times on this side. This is a product of two sets. Okay. Here, this times is multiplying this cardinality by this cardinality, and cardinalities are numbers. So the cardinality of A is a number, it happens to be 3. Cardinality of B is a number, happens to be 2, and we can multiply those two numbers in the way that we're used to, by just using the rules of multiplication by numbers. So here times is between numbers, here times is a product, a Cartesian product of sets. Okay. That's it for example 1. I'm going to go ahead and proceed through the next two examples here. Let me just copy that. We'll paste it in. Now let's go ahead and talk about example number 2. Describe the Cartesian product R times R, the product of the real numbers R with themselves, R. So what is the Cartesian product R times R? Well, in general, we know what a product of sets is. This comes from the definition of product. I said before this is going to be sort of one of the most important things. Maybe I'll just put a box around it to keep track of it. This is what the product is defined to be. The product of two sets. And whenever you run into something that looks like this, and you want to know what it's equal to, you can always refer back to this. It's equal to this. So with that in mind, here, if we want to know the product of R with itself, when we're writing R for the real numbers, we do it like that by hand. That's called blackboard bold. R times R. What is that equal to? Well, the definition says the following. It is equal to the set of all ordered pairs, A, comma, B, such that A comes from the first set, which is R, so A is in R. And then B comes from the second set, which in this case also happens to be R. So this is a way of writing down what that set, R times R, is. This is what the set is. And if you want to describe it, well, what is it? It's the set of all ordered pairs where the first element, A, is a real number, and the second element, B, is a real number. And thanks to René Descartes, we have this lovely idea, picture of what this means. We know what the real numbers look like. The real numbers, when we draw a picture of them, we make a number line, right? That's the real numbers. And when we want to make a picture of R times R, that is every ordered pair of real numbers, well, we just draw a real numbers going horizontally and a real number going vertically. We have sort of on paper 2 dimensions to work with, which means that we can do 2 copies of the real numbers in different dimensions. And then we assign every single point here an ordered pair of real numbers in just the way that you guys are used to. So for example, let me see. Ooh, I wonder if I could that over just a bit. Okay, there we go. If that's our origin, if we say go over 1, 2, and up 1, then there's a point right here. And this point is the point 2, 1, as you guys are used to. There's a point down here, which is, this point is, I think, -2, 3, and so on. Basically extending off in every direction. And the idea is that the plane, the Cartesian plane as we call it, when we draw the plane and when we plot points in it, when we use it to draw functions and so on, what we're really working in, that entire plane, is there is a spot on that plane for every single pair of real numbers. By pair I mean ordered pair of real numbers. If you give me any number to go first and any number to go second, I can find exactly one spot on this plane that corresponds to it. So what is the Cartesian product, R times R? This is the coordinate plane. I think that would be a good answer. You could also write this down as an answer, because that's what the definition says it is, but somehow getting into your head that when we say r times r, what we're talking about is the entire coordinate plane. The xy axes and all of the points in all 4 quadrants. Okay. Let's take a look at part 2. If A is the closed interval 0, 1, and B is the half-open interval 2, 3, draw a sketch of A times B. Okay, so now we're dealing with something that is hopefully familiar, but we haven't talked about in this class, which is interval notation. When you're dealing with the real numbers, for example, when you're dealing with this number line here, this is like the x number line, an interval goes between 0 and 1. So this interval here goes between 0 and 1. The square brackets, the brackets on the end are either going to be square brackets or round parentheses. And each one will correspond to the endpoint on that side. So that square bracket by the 0 means that we're going to include the number 0, and then all of the numbers bigger than that until we reach the number 1. And then we're going to also include the number 1, but nothing beyond it. So this is all the numbers from 0 to 1, including 0 and including 1. This one is all the numbers between 2 and 3, including 2, but not including 3. So we could include, for example, 2.5 and 2.9 and 2.999, but we're not actually going to include 3. So I just want to talk about this this product. I'm going to write it as a product first, and then we're going to try and see what it looks like as a picture. So first, let's talk about the product. This is A is equal to this 0, 1. B is equal to 2, 3, and this is part 2 of this question. All right. So if we want to know what is A times B, well, since we have notation for these sets, we can just use that. Instead, A is the interval 0, 1, and that's times B, which is the interval 2, 3. And what is that equal to? Well, it's equal to a set, and it's a set of ordered pairs, A, B, where what happens? Well, the first thing, the A, has to come from our first set. So A has to be a member of 0, 1. This is just from that definition of Cartesian product. And similarly, the second thing, B, has to come from our second set, 2, 3. So let me give you some examples of things that are in A times B. So examples of members of A times B. Here are some things, if you looked inside it, you know that A times B is a set, and if you looked inside, you would find, for example, the ordered pair 0, 2, and how do I know that this is an element? Well, 0 has to come from the first set. If we look at this product, the first element has to come from the first set, and the second element has to come from the second set. 0 is a member of this set. 2 is a member of this set. Okay, some things to be aware of. Thing number 1. These sets don't look very big, okay? But don't be fooled. This is not just a set with 2 things in it, 0 and 1. It also has all of the numbers in between 0 and 1 in it. So this simple notation is a set that contains 0 and contains 0.5 and 0.9 and 0.6823 and 0.99999 and 1. So every decimal, every fraction, every irrational number, every real number in between 0 and 1 is included, as well as 0 and 1 itself. So this notation for a set is very deceptive. It looks small because you can write it in just a few symbols, but it really represents a set that has infinitely many things in it. All infinitely many points between 0 and 1 are in this set. Similarly, this set, the interval from 2 up to 3, which includes 2 and doesn't include 3, it includes all of the infinitely many decimals in between 2 and 3, including 2, but not including 3. Okay, so this is an infinite set, this is an infinite set, and the product of them is going to have infinitely many things in it. So I've given one of the things, which is 0, 2. I strongly encourage you to pause the video now and just write down 10 more examples of things that are going to be in this A times B. Okay, if you did pause the video, good for you. And I'm going to write down a couple of them now. So, for example, 0.5 and 2.1, 0.68 and 2.5, 0.00783. Oops, oh, I don't want to do that. Here we go. That's only one item, and I need to make an ordered pair, comma, 2. 0.1, comma, 2.999, etc. dot dot dot. That's those dangerous dot dot dots because they just mean continue like this. I certainly have not listed all of the members of this set 8 times b. I've only listed, let me see, how many ordered pairs? 1, 2, 3, 4, 5 ordered pairs, but there's a lot more. There are infinitely many. Okay. So let's go ahead and try to see, the instructions for this problem said to draw a sketch of that a times b. So let's go ahead and make a sketch of that a times b, and let's see what it looks like. Let's draw coordinate axes again. So let's see. Okay. And just to put in some marks, the dots are already on there, but just to make that really clear, on the x-axis, this is 0, 1, 2, 3, 4. On the y-axis, this is 0, 1, 2, 3, 4. And the question is, where is it, if we want to plot these points, where do they go in our picture? And so I'm just going to plot them in the usual way. Some of them are decimals, which means they're going to be a little hard to estimate exactly where they are, but we'll just do our best here. And we'll just use a different color so it stands out against my axes. Okay, so let's look at this. I'm just going to plot some of these points, and then from that, try to figure out what this thing looks like. Remember, what we're trying to draw a picture of is this product right here. Okay. So, let's go ahead and plot 0, 2. That's the first ordered pair here. And that is going to take place here, where x is 0 and y is 2. We just draw that in the usual way. That's 0, 2. 0.5, that's coming over to about here. And then 2.1 is going to be just a tiny, tiny bit about it. It's going to be right there. So that's about right there. 0.68 is even farther over towards 1, but not quite all the way there. So 0.68 is somewhere in here. And then 2.5 is going to be, let me see, this is 2, this is 3, so it's going to be halfway in between. It's going to be about right there, 0.68, 2.5. Let's go ahead and plot that one in. And then 0.00783, this one is really close to 0. And this is exactly equal to 2. And that means, let me see, really close to 0, but a tiny bit above. And then the y, so on the x, it's just a tiny bit to the right of the origin. And then up above, we're at 2. So it's right next to that other green dot. In fact, it's so close, they probably just would overlap each other in this picture. And we'll do one more, 0.1, 0.1, and then 2.99. That one is going to be right up there. So you'll notice, first of all of these points seem to be in this area. Yeah. Secondly, things to notice. Well, I'm going to go ahead and zoom in a bit. Things we want to notice here are that when we deal with these points, the x-coordinates of all of these points, the x-coordinates all are coming from this interval 0 to 1, which means that no matter what we plot in these points, all of the x's are going to be in between 0 and 1 on the x-axis. You can see that if you think about the part of this board that's between 0 and 1 on the x-axis, it's right here. It is indeed between the 0 on the x and 1 on the x. Okay. Similarly, on the y-coordinates of these, the y-coordinates are coming from the second set. Yeah, the second coordinate comes from the thing after the times sign, which means that the y-coordinates are all between 2 and 3. So on the y-axis, the y-coordinates are going to be between 2 and 3. They might include 2, but they will not include 3. And what does it mean when we actually fill in all of those? Well, every single point in here that has an x-coordinate between 0 and 1, and a y-coordinate between 2 and 3, every single one of those is going to be filled in. So when we fill in, we need to fill in, for example, all of these. These are all points where the y-coordinate is equal exactly to 2, and the x-coordinate is all the different things between 0 and 1. And of course, we can fill up from that because we're allowed to change y, the x and the y, as long as x is between 0 and 1, and y is between 2 and 3, and we're good. So it's sort of like we're filling in a little rectangle here. Now, we don't go quite to 3. We go all the way up, but not exactly to 3, and that's often done by putting a dotted line. That's a little bit hard to see. I tried to do my best to do a dotted line at the top there. But on the left side and the right side, we go all the way to 0 here and to 1 here, and this is where y is equal to 2. So this is a box. It sort of has 3 flat sides and then 1 dotted edge up here, and it's all filled in the middle. And that's somehow the proper way to draw this set A times B, where A is the closed interval 0, 1, and B is the half-open interval from 2 to 3. Okay, that's it for our example 2, part 2. Oh, just revisiting the question, if A is the closed interval, draw a sketch of A times B. Okay, let's talk about number 3. I don't seem to have the magic touch for pasting. Okay. Boy. Touch. Okay. Well, we're just going to move it on down then. Here we go. So, let me see if I just do a little cropping, I can reveal the last part of this question. Here we go. Cool. Let's talk about 3. For this problem, we're talking about, you'll see in the end, we're talking about A times B times C, A times B times C. So now we're talking not just about a product of 2 sets, but of 3 sets. And in 3 sets, instead of an ordered pair, you have an ordered triple. So this set right here, A times B times C, it's going to consist of ordered triples, like you were working in, say, 3 dimensions, where the first element is from A, the second element is from B, and the third element is from C. Here, the set A is a set from, it includes 3 and includes 7. This is not interval notation. It doesn't have square or round brackets. It has those set brackets. So this set A really just consists of those 2 numbers. It doesn't have anything extra in there. Similarly, the set B is just these 2 numbers, 2 and 4, and the set C is these 2 numbers, 5 and 9. Okay, is 3, 2, 9, that's an ordered triple. So it's in round parentheses, and the things inside are put in a particular order. They're separated by commas. Is that in A times B times C? Well, in order to check that, what we need to verify is that in this ordered triple, the first thing is an element of A. So is 3 an element of A? If we look at A, 3 is in there. So that's good. So for this one, 3 is an element of A. Check. Similarly, the number 2, the next one, is an element of B. Well, we can look up here at B, and you see that it is, since B has 2 and 4 in it, it's true that 2 is an element of B. And then finally, is 9 an element of C? And you see that it is, C includes 5 and 9, so 9 is an element of C. So the answer to this number 1 question is yes. Question 2, is 3, 5, 2 in A times B times C? Well, we have, is 3 in A? Yes, it is. Is 5 in B? 5, we would say, is not in B. And that means that the answer to 2 is no. In order for that answer to be yes, in order for that ordered triple to be a part of that Cartesian product, you would have to have the first in the first set, the second in the second set, and the third in the third set. And once one of them fails, 5 is not a member of that second set B, then we're already done. We don't even have to check the third one. Okay. So that's our answer to example 3. You guys will have some problems of your own to work on that are similar to this. Give them a try, and don't hesitate to reach out to me if you have questions.